And the way I like to put it is that we have found the hydrogen atom of quantum field theory. What I mean by the hydrogen atom is a system that is simple enough so that you can solve it exactly on a few lines. An integrable model that has extra symmetries that are powerful enough to completely solve the theory. But it's a good approximation to the real world. And such models, like the hydrogen atom, have played a fundamental role in the history of physics, if you think about it. Especially the problem of the two-body interaction, a system that contains just two bodies, or one if you remove the center of mass, with an inverse square law force. That gave rise, the existence of such a simple system, like the Earth going around the Sun or the Moon around the Earth, gave rise to classical mechanics. It really would have been hard to see how Newton would have developed the laws of classical mechanics if he didn't have this simple integrable system to work with. If he had some, chaotic dynamical system, it would have taken at least another 20 years, or 200 years. The Bohr model was based, in fact, the success of this first model of the atom, almost 100 years ago now, was based on the fact that the hydrogen atom is an integrable system in quantum mechanics. So Bohr was able to write down semi-classical approximation to a theory he didn't have yet, which was exact because of this integrability. And, it's hard to see without a simple integrable model how quantum mechanics would have developed so rapidly. Non-relative, that was true, actually, still integrable when quantum mechanics was discovered. It was true for the Dirac equation of the hydrogen atom, whose, again, precision, you could calculate exactly, and discrepancies with that led to relativistic quantum mechanics and quantum electrodynamics. Well, we haven't had in the study of the nuclear forces or physics beyond non-relativistic quantum mechanics many nice examples of integrable systems. A lot of two-dimensional field theories which informed us about the structure of quantum field theory, renormalization group, etc., etc. But not many examples in 4 dimensions until now, and now QCD, of course, became closer and closer to an integrable model at very large momenta, and that's extremely important because it gives us the ability to calculate, for example, LHC backgrounds. So at least we have an integrable, trivial, free field theory, almost. But that's the only example until recently where n equals 4 supersymmetric gauge theories, just the gauge theories we use in the standard model, but maximally supersymmetric and in the limit of infinite colors, it appears integrable and completely soluble and almost solved. And it is a good approximation to the real world. To actually make contact with the real world, we have to break supersymmetry, put in quarks, expand in 1 over n, and that'll take some time. Not only that, it is dual to a string theory in 10 dimensions. So this, I believe, and the reason so much of research in string theory and quantum field theory has focused on this duality and on this theory, is that it can play the role, has been playing the role of the Earth-Moon system or the Bohr or the hydrogen atom. It's not only beautiful, this connection, this model, but useful. It forms the basis, starting point for calculating important, phenomenologically important amplitudes, QCD scattering amplitudes. It informs us about the quark gluon liquid using the correspondence with string theory, and now many-body theory, condensed matter physics, ADS-CMT. It's not only useful, but important, because it connects to many of the deepest issues we encounter in our attempts to understand quantum gravity. Black holes, the Big Bang, emergent space, all of these deep issues on the gravitational side of physics, we can approach now using this, starting from this integrable quantum field theory. And it informs us as we try to understand the connection between the ways of looking at string field theory about field theory and string theory.